Thank you very much. Very nice good morning. Well, we heard about 3.2 degrees, glide wings, and now I would like to report on 4.5 and 3.2 degrees. And this is a research project that was carried out in our institute. And Mr. Mollwitz was in charge, and I may report on it. Reinhard König this morning gave you an overview of older projects that took place earlier. I would like to refer to the same project, Quiet Air Traffic 1 and 2, and Quiet Approach and Departure that we carried out in till 2005 with other partners. And one motivation reason for us was to get the source of noise, that is the airplane, furthest away from people who live close to airports. That means as high as possible, and that would lead to steeper approaches. There are limits, however, especially if I want to land. And at that time, we had the idea that at the last end, we wouldn't do anything. The last 1,000 feet would always be in 3.0, but before we will go steeper and we'll have a steeper approach further up. In order to have a steeper approach, you have to configure it differently. At that time, we thought of complete configuration in order to get the optimum per aircraft, that is per every aircraft and individually, configuration, landing speed, etc. We tested that, we made the approaches, and we had angles of 7.5 degrees with the A33 simulator in Berlin. Right, so we did that, but then we found that you should not fly it manually. Better not, because if you make a mistake with the top of descent, you don't have a chance to hit the ground properly. And therefore, we programmed it into our internal FMS system, and with the VV614 Atlas plane, we tested that, we flew it, and we got some requests from the air control when we entered Braunschweig. You don't want to land in Braunschweig, they said, because we were too high. The altitude was much higher than normally. We said yes, and we landed. So you can do that. That was our message at that time. You can do that, and it was accompanied by noise calculations. And the result was, yes, there is a benefit. And then it was forgotten somehow. That was back in 2005. And in 2011, we took it out of our shelves. Not the steep segmented approach, but we had the chance to do the trial in Braunschweig with Air Berlin. And we asked them to have steeper approaches. We had some measurement microphones, and we measured the noise level. And then when we found that it worked, but the pilots didn't want to have 4.5 or 5 degrees, we made precision supported landing with GBAS, steeper approaches. And we found that this was possible. And with all that knowledge in the background, in the expert body, active noise abatement, we discussed it, and there were further deliberation, and now this research project was started that I'm going to report on right now. And a lot of simulator trials with Lufthansa, Condor, TUI Fly, etc. followed suit. And on the 4th of October 2013, that is 3-4 weeks ago in Frankfurt, we also started flight tests with Condor. That was the overview. Here you can see some further data, beautiful data. In 2011 in Braunschweig, we had steeper approaches of 3 degrees up to 5.5 degrees with a 737-700, and there were 2 points where we had measurements, and there were differences of 3-4-5 dBs with the differences. The distances here, and that's really happy. That's really positive, but there were only a few measurements that are not representative. That was a trend where we said Yes, that's good. The research project as such has several parts. The first part has been concluded. We studied together with pilots, with our own ideas, our internal people. So we wanted to find how the vertical profile of the steep approach would be designed, that we can not only do it with our systems, but also with systems that are available in aircrafts today. So this is what we tested in the simulators. And as it worked so positively, Condor said, we want to fly it. So they made an aircraft available. And together with Deutsche Flugsicherung, with Fraport, with the Umwelt- und Nachbarschaftshaus, we did it on the 4th of October and really actually flew it. Now, we looked at all possible vertical profiles, how you could fly them. We elaborated several variants, and then intensively in several workshops we met pilots, talked about it, and all rules and regulations that we found were used. And we produced fewer variants and tested them in the simulator, again, 2 or 3 of them, and then we came up with the final design. The workshops were carried out with Lufthansa, Condor, Air Berlin, TUI-Fly, and pilots of different airlines that belong to the cockpit group. So 75 pilots, highly experienced, and many different patterns were really looked at. A320, the Q400, etc. You know, it was really great fun to do it together with the pilots. Thank you very much to you. In the simulator, we were with Condor, TUI-Fly, and Lufthansa. 767, 737, and A320, A330, A340, A380, and B747-800. So all these aircrafts flew that route. We start with 8,000 feet, not 5,000 as we do today, and then with 4.59 degrees we descend. You might ask, why 4.59? It must be under 4.5. So if I do it at 4.5, and they have published glide angle, slope angle, the plane has to prove that this angle plus 2 degrees more can be flown stationary without acceleration. Under 4.5 degrees, this is not necessary. So that's a decent limit. So 4.49 degrees were the result then. That's what we did. Later on, we would like to land with a 3 degree on ILS. So we need a transition between the 4.49 degrees and the 3 degrees. So that at the latest, with the typical height of 1,000 feet, we would be completely established on the final approach. That is landing configuration, respective landing speed, everything should be in order at 1,000 feet. In order to have some margin left a bit earlier, if you calculate it backwards, this bending point should be at 1,500 feet, and then you can do it that way. In theory, 1,300, 1,200 should be sufficient, but then probably you don't have that much of a buffer. So 1,500 you know, should be it. So there is still some room there. And the other result was, and you should not fly manually, everyone agreed, not fly manually, especially as I most of all would have flown 5, 6, 8 hours before, so it shouldn't be too complicated. The steep segment, if possible, should not have set the landing gears as yet. But that would mean, depending on wind situation, my speed should be kept with the flaps. So as a pilot, I can leave a lot to the plane, but speed management cannot be done by the FMS, as it does not have access to the flaps and slats. That's the task of the pilot during the steep descent, to monitor speed and then set flaps and sets in order to adjust. The vertical profile the FMS with Bahrain arena. That's the one precision approach. And if we want to land, we have to do it as a Bow-Wiener transition to ILS approach. We have to define it that way so that we can capture ILS and do an auto land. That's the idea. We tested it in the simulator, where we had the average speed for the steep segment of 400 knots, so it should not be too much for ordinary traffic situation in Frankfurt. And then 170 knots, sorry. And then we determined certain conditions for the plane and the crew: 40 degrees, higher temperature, and 25 knots tailwind were added to the steep segment. We heard tailwind with steeper approaches. You know, it's not so pleasant, but it's possible. You can fly it. Also with the landing gear not set. It was possible with the A340 and also the B767. Without tailwind, also with non-set landing gear, we can do it with the A320, but not at the high temperature. And we can also do it with the B7478. The only plane that required a different procedure is the 737. Which would fly it only with landing gear not set, with headwind, sufficient headwind. Otherwise, the landing gear should be set already in the steep segment. But even if we have unfavorable conditions, also with the 737, with 25 knots tailwind, max landing weight, the 4.5 or 4.49 degrees can be flown. We can do it. It's possible. And this is what we produce in terms of results in the simulator. Flyability, limits for wind, etc. For the A320 we didn't do it, but for the A330, 300, 600, A380, 737, and 747 and 757 with slats and flaps, and that also allow the use of spoilers. And that's why there are differences in planes. Third position of flaps do not allow the use of spoilers. Certain configurations, gear up or gear down, and flaps don't allow the use of spoilers. But the result was also, as we saw in the A330 in the simulator 10 years ago or so, can do it very steeply with sets and flaps and landing gear not set, and the others are at 6 degrees or 5 degrees. So 0.5 degrees above the 4.5 degrees. That was our target. But the 747 is a bit different here. It's reaching its limit. Okay, the pilots, they didn't have experience with that. But after a short period of time, they were surprised. And basically, they accepted well. Well, they said it's possible. When I told my colleague this morning what I'm going to fly in the night, they said, "You're insane, you can't do that." And now, I should say, it works. That's what the pilot gave us in terms of feedback. But, of course, you should say, understandably, with tailwind or high temperatures, there are some reservations among pilots. But this is understandable. Well, because it's really a challenge. Now, how does it look for Frankfurt if you do it that way? It's about altitude. And if you land on the northwest runway, then instead of 5,000 feet, you are at 8,000 feet, 900 meters height. And this is a reference to the 3 degrees. It would go to Niederrad. And they're only 15 meters high, and that's the normal route. the normal path. Those who know that region, west of the airport, Abatement, or what is it, Großwinterheim, the 3,000 feet higher, but then I go down slowly, and at around Hochheim, I'm about 30 meters higher. All right, so far so good. Condor was very much convinced that it would work, and then they said, all right, we would like to fly it. Took a bit till we all got it organized with the air traffic control and the airport management and the Umwelt- und Nachbarschaftshaus. But finally, on the 4th of October, it started. We flew that machine, and we put much more fuel in than necessary in order to have a normal landing weight. And then we not only had our team on board, but a lot of journalists and others who wanted to participate in this project. The DFS put it in the nice picture here. They didn't embellish it. No, I didn't want to say that. For the landing direction 07, which was not so favorable. We wanted to do it in Frankfurt as we had so many measurement microphones because of the 3.3 degree. But all right, at that very day, we had the wind situation as it was. Come back to the wind situation later on. The steep segment starts at 7.5 Nordic miles before touchdown and 4.5 Nordic miles before touchdown, it would go into the normal 3.0 degrees. This is a map once again. So I can see, does it work? No, unfortunately not. Oh, well, there's a laser pointer, so I can show you. Normally it should work. Here you are. I don't see the mouse, so if someone else shows, I never see how it works, so I rather prefer the cursor. Here above Hochheim, we are at the ordinary altitude, normal altitude, and here we start with the steep descent, Oppenheim. That was our flight program. We had hoped that we could reach 6. I mean, we were doing so well that in ordinary traffic situation, 9 of these flights could be organized. 2 were done as a standard planned with 3.0, but we always flew 3.2 all the time. So 2 reference flights, 1 and 8. And then 6 flights were operated in our selected procedure with flaps, 20 flaps and spoilers, for speed management and gear up. Then we made another flight. The original idea of the DLR was used with a much lower speed in the final configuration, 140 knots, and it was always 4.5 degrees, flap full and gear down without the use of spoilers. I always said it was 3.0 degrees, that was the design, but actually we were at 3.2 degrees all the time. Also the reference flights were 3.2 degrees. That's the altitude profile. It's quite nice. You can see what flights flew 4.5 degrees and which flights were at the standard of 3.2 degrees. And here you can also see quite nicely that the vertical profile was kept continuously. And now we had landing direction 07, yes, up to 1,000 feet above the ground. And we had headwind with 1,500 feet. However, the wind turned. And there, you know, at this high altitude, we had up to 20 knots tailwind. During these tests, we did it for the very first time with a lot of journalists on board. And basically, for this procedure, we had adverse conditions. But still, you can see with the vertical profile, it worked out really fine. The speed profile looks a bit different. The top 2 lines, there we were more speedy. These were the standard reference 3.2 degrees, and the lower red one, also nicely put. That's the one with which we were permanently in landing configuration, 140 knots. And then we made a mistake. We thought 170 knots would be good, but with this load, with that weight, for the 767, 160 knots would be the reference. So we flew the 160 knots, and they adjusted it with the spoilers only once. You can see that there is a peak here. Here, the one pilot did not control speed fully. In the vertical profile, it didn't show, but the machine did it. Sorry that I have to say it. For a non-testing pilot, it's unusual to do 7 to 9 approaches, one after the other. And even for the flight crew, it was quite awkward. They say, prepare for land, sit down, out, etc. For them, they had to repeat it again and again. But it worked excellently. This is the lateral profile. Only once we went into rolling. For the traffic situation, it was really fit. Excellently, we land, go around, headwind, departure, up and come in again. Once we turned in too early with the reference flight, not over Abatement. We didn't flow over Abatement, and there you can see what was measured there. There was one station there. On the left-hand side, that's the maximum noise level for the one reference flight, measured for the one reference flight, and then compared to the steeper approaches. There we were 3,000 feet higher. And I mean, it goes without saying that then we would have reduced noise levels. That's the 6 dB that we had wished for, and that was really materialized. I've got also the median value of the measurement line. I don't have a sophisticated dB arithmetics. I mean, we heard yesterday that it's not so easy to do that. Of the 6 measurement values, I produced an average, a mean value, but the scattering is also quite obvious here. 1 to 2 dB. With different approaches and the same speed, same altitude, same configuration, still they produce different results. On the right-hand side, you can see the time evaluated figure, and in the landing configuration approach, it's not so good. It's clearly slower, so noise is on the measurement point much longer, and you can see it with the lags here. These are the other measurement stations of the T09, 209, 14, 88, and 11. You have seen them before, and I just click through the measurements that we carried out. And here, 20999 Mainz, we see a 209 Mainz, we see a reduction. You could look into it, about 2 dB with the maximum noise level. With Gustavsburg, and that's interesting, measurement point 208. It's a bit closer by, not so far away from measurement point 209. I mean, they are really close by, basically. But still, we have 4 dB here, repeatedly, around about 4 dB. I'm not an expert in noise measurements. That's obviously normal. That there is some kind of scattering in noise measurements. But anyways, we will have a closer look at the data that we have from the cockpit and then correlate them with the route data. But as we only had them Friday afternoon, and till Sunday evening we had to do this evaluation. So I can't really show you the correlated data. So it takes a bit more time to have a more precise evaluation. In Hochheim, we are at the normal altitude, maybe a bit higher, but not that much. And this is reflected in the measured values. And also you can see here, with the 6 approaches, that there is a big scattering. You cannot easily explain this big scattering, as it was the same altitude, same speed, etc., with the same configuration. The wind changed, however, probably that's the only point that influenced it. I can't really say. but in principle terms you can see that here. And then here, this point that was designed basically to set the landing gear, etc. Here we only had a very, very small change of fluctuation. I mean, if it's statistically significant, it's not significant here. It's more or less the same. Flursheim, this is really what we didn't want to see at all. Now, if we compare all the measurements there, it became a bit more noisy. That's not really easy to explain. Same configuration, same speed. Why was it? Probably you can have a closer look at it. And here at the right-hand side in the table, I put it, the altitude differences at the different measurement points as an average here. Oppenheim 3,000 feet higher, Mainz 370 feet higher, Gustavsburg 217 feet higher, Hochheim 22 with the measurement point 88, mobile measurement point 88, it was 7 feet less. And Flursheim we were 20 feet lower. It's not that we just went down too quickly, but the one reference flight flew a bit higher. Well, and if you produce a mean value, then that's the result. So it was at the upper limit of the 3.2 degrees. What you see here, once again, is a trend analysis, but be careful with it. We started with Oppenheim, started the measurement with Oppenheim, that's the left-hand side point with 3,000 feet difference, and the mean was then 5.5 dB quieter, and with smaller altitude differential, you also had clear noise reductions. Just to give you the results, there were two tasks that we had to fulfill, whether it was flyable. We had to determine whether it's flyable not only in the simulator but in real life. And here we can tick it off. Yes, it's flyable, especially during the conditions that we had. And we also had manual speed control. The pilots could adjust the speed manually with the setting of spoilers, so they could keep the speed. Also, to make sure that always at 1,000 feet they were established. That was all okay. According to the airline procedures, all of them were in a position to land. Of course, we have to change the airline procedures, not only airline procedures, but glide path intercept from above, and this is what we also have to do internationally. Noise measurements, okay, there were only a few data available, definitely not sufficient to have to produce a statement that withstands further tests. We could demonstrate, right, there is a noise reduction, there is a trend. If you live more than 10 kilometers away from the threshold, you will have a benefit, but we have to do more. Right, thank you very much.
Several questions, but we will allow only a few. So over there, over there, the microphone. To Mr. Kröger. He was the first one raising a hand. Raise a hand again, Mr. Okay.
The guy from also control was behind me. We had several line of sight conflicts here in getting the word. Well, once I state something concerning the 3.2 degrees approach, which is done in actual operations, you won't possibly be disappointed if I don't say anything concerning the 4.49 degree trial approach. As you mentioned, it has been designed and started as a research and development trial, I would say. And even among our group, there are some very keen pilots doing these things. I personally haven't taken part. I actually can't imagine that these things work with so much tailwind. There might be some considerations. In German, I would say, let's try an Elchtest, doing these things in real life. So we are far from that, and I can imagine what we can read in the newspapers tomorrow. So there's a big Erwartungshaltung concerning these things. So you need to be the one on the brake. What I want to ask you is, we see it very positive. Condor is doing these things with just a more or less empty plane. However, if there are journalists on board, are they passengers? Have they been declared as crew? Are there passengers on a flight and research flight? And I have seen a document from a major airline not being home-based in Frankfurt, but also being mentioned in this folio. They publish a flight bulletin defining these procedures, and from that I have the imagination they are done in actual line operations. Can you confirm on this? Thank you.
Ja.
Yes, I can. The 4.5 degrees, you know, of course, that was unusual, but it worked here with a tailwind as well. How Condor did it exactly? We had a full crew there. The journalists were passengers. I was a passenger. All of us were passengers there, except the pilots that flew the plane. And we didn't have an empty plane. We had so much fuel on board that it was the ordinary landing weight of a 767 if it comes from any destination to Frankfurt. And the other one was Hanover, TUI-Fly. TUI-Fly also participated, and they liked it as much. And there we do something on top. And this is in the steep segment, a radius to fix term onto final. The TUI-Fly aircraft would fly the 4.5 degrees steep in the radius to fix turn, and then would go to the final approach. In agreement with DFS and BAF and the airport of Hanover, we would like to accompany that with noise measurements, but we were not sure whether we put the microphones on the right points. And they do it with ordinary patients when they land from the southeast.
Time restrictions we have.
Bertolt Vogt, Bundesverein gegen Fluglärm.
I think the theme that will prevent to use it in Frankfurt was already hinted at, speed control. DFS is really afraid of any sync approach, because there you can control speed only with great difficulties, and therefore there are the long horizontal flight over the Kinzigtal and Rheinhessen at low altitude, and the weak point is speed brakes are not integrated into the speed control system, which is only impacting thrust. And I hope that the aircraft manufacturers are still around. Maybe they can take up this idea that as quickly as possible, the speed brakes should be incorporated into the speed control system of aircrafts. Maybe a short comment. A390 for London Heathrow, the spoilers are included in the speed profile, and the second thing is also considered in the other part of our study, because we want to do it in ordinary traffic situations with procedures like that. I hope the second study will come.
Watch and make very short questions. The man with a raising hand who would be tired in a minute. Okay, give him. No, he was the first one. Over there, the one who, so please. Ja, no, Sie sind dran.
Seems to be me, yeah. Thank you. Christian Woborski, my name, Austro Control, still active air traffic controller. And listening to this interesting presentation, I was just trying to imagine to make this thing happen. Because you create a big expectation here amongst people not so well known with technical backgrounds. And nailing aircraft down on a standard transition arrival at 8,000 feet, having almost no influence on speed control. First judgment from my side is you cut back the capacity anywhere between 30 and 50% on any major airport. So my question is, did you evaluate the impact on a day-to-day operation, not just with a single aircraft, but an airport like Frankfurt, Munich, and many, many others? And I want to stress this once again, capacity cutback of 30 up to 50%, first guess.
Well, two answers to that. First answer, the results that we have are not that bad that we would say we would stop it. So we would like to continue, and we'll come together very soon in order to find what we can do, what we have to do, and what the next steps will be, what the opportunities are. And the second answer, same as before, how the integration is, what capacity impact will be produced. Well, the plans are there to study that, and it will hopefully happen if it can be financed. And we've planned it for next year, but we don't know whether the finances are there. Hybrid traffic, capacity analysis, etc., as presented in the project plan.
Yes, you.
My name is...
Then I have to, okay, but then it's finalized. So you, and then it's...
Okay, Herr Korn, vielen Dank. Mein Name ist Sebastian System.
Thank you very much. Ich komme aus Deutschland. My colleague had the same question. It's about capacity. I followed it with keen interest, and I'm convinced that there will be noise reductions as a result. As you have shown in your graphs, the average speed is 20 to 30 knots lower than the ordinary approach, and over a longer approach route. With the same separation, will that lead to capacity reductions? Can you do something against that? Can you increase the speed? Short answer. I would also try it with the airspace structure, separate laterals and then R&P processes in combination in order to avoid different speeds flown at the same time.
Ja. Dirk Fieber, mein Name, pensionierter Lufthansa.
Pensioned Lufthansa captain. I would like to take up what my colleague has said. You have created expectations. Everything that helps us in terms of noise reduction should be okay. But the 4.5 degrees, they were flown by pilots that had already 10,000 hours flight experience, and they said it was no problem. I myself have 14,000 hours on the 747, and one criterion as training captain was to expect from a potential pilot that they can stabilize a high steep approach. And this is really demanding in terms of flight capabilities, flight skills, and therefore I have my reservation in daily operation for all aircraft on pilots of the world. That's highly demanding, and the question is whether you can spread it and to what extent you can spread it. And you said that the project might be implemented in 7 to 10 years' time, and that's you have taken the second step before the first one. The CDA approach can be designed as it's done globally in London, as we've just heard, as it has been practiced there for a long time, not only in London, but in all British, at all British airports. But probably someone else needs to answer that question, whether you have taken efforts also to do the CDA approach in the conventional manner. Das würde ich
like to say, of course, you can always think about risks. But consider if we had the first consideration like that when we were still living not in our homes, but in some holes. It was very risky to go outside. And therefore, I think we always have to try what we can do. And then we have all the measures, and DLR has the measures, to decide, is it really dangerous? And then, of course, we cannot do it, safety first. Quite simple. But on the other hand, not to try, would be the totally wrong decision for research and development at least, and I think also for the future of aviation as a whole. So I would like you to go a little bit more in that direction. Okay, this is because I'm the head of DLR, I mentioned that one. Okay, now we come